We're asked to consider the vector field f, determine if the vector field is conservative. If it is, find a function little f so that the vector field f equals the gradient of little f, which means f of x comma y would be the potential function, and then finally use the potential function to evaluate the line integral along the curve c of f dot differential r, where the curve c is defined here. For a quick review, if we know that a vector field is conservative, it will make evaluating a line integral much easier. The integral of a conservative vector field is path independent and only depends on the endpoints. A vector field f is called conservative if it is the gradient of some scalar function little f such that the vector field f equals the gradient of little f. And again, f is called the potential function of the vector field f. The test for a conservative vector field in a plane is stated here. If p and q have continuous partial derivatives on an open disk R, then the vector field f with components p, q is conservative if and only if the partial of q with respect to x equals the partial of p with respect to y. So if the given vector field is conservative, then we'll be able to evaluate the line integral along the curve c of f dot differential r using the fundamental theorem of line integrals. Let's first determine if the vector field f is conservative. Well, using our notes below, notice how p is equal to 4x plus 3y and q is equal to 3x plus 2y. So if the given vector field is conservative, then the partial of q with respect to x must equal the partial of p with respect to y. So the partial of q with respect to x is equal to the derivative of 3x plus 2y with respect to x. Well, the derivative of 3x with respect to x would be 3. The derivative of 2y with respect to x would be 0, because we're treating y as a constant. And now the partial of p with respect to y would be equal to the derivative of 4x plus 3y with respect to y. Well, the derivative of 4x with respect to y is 0. The derivative of 3y with respect to y is 3. So because the partial derivatives are equal to each other, we now know that the given vector field is conservative. So this first answer is yes, the vector field is conservative. Now let's work on determining the potential function. Again, we now know the given vector field is conservative. We want to find little f of x comma y such that the vector field f equals the gradient of f. Remember, the gradient of f would have an x component that's a partial of f with respect to x, and a y component that's a partial of f with respect to y, which means 4x plus 3y must be equal to the partial of f with respect to x, and 3x plus 2y must be equal to the partial of f with respect to y. So to reconstruct the potential function f of x comma y, we'll integrate the x component with respect to x and the y component with respect to y. So here we'd have the integral of 4x plus 3y integrated with respect to x, and here we have the integral of 3x plus 2y with respect to y. So this integral will recover the x part of f, and this integral will recover the y part of f. Integrating with respect to x, here we'd have 4 times x squared divided by 2 plus 3y times x, or 3xy. Now here we're only recovering the x part of the equation, so we could still be missing y terms and a constant, so we'll put plus g of y to represent a function of y. Simplifying, we have 2x squared plus 3xy plus g of y. Now here we integrate with respect to y, so the antiderivative of 3x with respect to y would be 3x times y, or 3xy, plus 2 times y squared divided by 2. Here we're only recovering the y part of f, so we could be missing a function of x, so we'll put plus, let's say, h of x. Simplifying, we have 3xy plus y squared plus h of x. Now by combining this antiderivative and this antiderivative, we can recover the potential function f of x comma y. F of x comma y is going to be equal to, well, here we have 2x squared. Notice how both antiderivatives have the term 3xy, so we have plus 3xy And then we still have a y squared term here, so plus y squared, and then plus a constant of integration, let's call it k. So notice how by combining these two antiderivatives, we recover or reconstruct the potential function f of x comma y. So going back to our first slide, we now know the potential function f of x comma y is equal to 2x squared plus 3xy plus y squared, and the plus k is already here for us. Now we'll use the fundamental theorem of line integrals to evaluate this line integral. The fundamental theorem of line integrals states that if we let C be a piecewise smooth curve lying in an open region R, given by the vector function r of t, if the vector field f is continuous and conservative, then the line integral along the curve C of f dot differential r is equal to f of x of b comma y of b minus f of x of a comma y of a. Remember, f is the potential function of the vector field f. So essentially this is telling us that if the vector field f is conservative, then the line integral between any 2 points is a difference in the values of the potential function f at these points regardless of the path used. So again, here's the given vector field, and here's our potential function. Our curve C is defined by r of t shown here. So notice how x of t equals t squared, and y of t is equal to t cubed. And t is on the closed interval from 0 to 3. And now using the fundamental theorem of line integrals, because we know the vector field f is conservative, this line integral is equal to little f, the potential function of x of 3 comma y of 3 minus f of x of 0 comma y of 0. We'll notice how x of 3 is equal to 3 squared, which equals 9. Y of 3 is equal to 3 cubed, which equals 27. And both x of 0 and y of 0 are equal to 0. So here we'd have f of 9 comma 27 minus f of 0 comma 0. So using the potential function, we would have 2 times 9 squared plus 3 times 9 times 27 plus 27 squared, and then minus, when both x and y are 0, notice how all the terms would be 0. So we'd have 0 plus 0 plus 0. Simplifying 2 times 9 squared, that's 162, plus 3 times 9 times 27 is equal to 729, plus 27 cubed is also 729, which is equal to 1,620. So notice how by determining the given vector field was conservative, we were able to evaluate this line integral by evaluating the potential function at the end point, then the starting point, and then find the difference of these two function values. I hope you found this helpful.